So let's talk about digital signals and analog signals. Now, digital signals are those signals that have specific values. We call it discrete values. So discrete values means in this case we are going to use ones and zeros. It's either 1 or a 0, there's no in between. Like for example, this is called a digital signal because it's either 1 or 0, that's it, nothing in between. Whereas an analog signal is a continuous variation in the values. So you can move up here, down here, so you can be any values in between. That's called analog. Now most of the signals that we produce are all analog. And now what they do is they have to convert to digital first, but then later on when you want to reproduce a signal, let's say to watch TV or to hear music, in the end we still have to convert back to analog one. Alright? So let's talk about the advantages. Why do people still want to do digital? Because whenever you use digital signals, that means you would involve an extra process. You would involve you converting your analog to digital first, transmitting or storing it or both, and then later on when you want to produce back the signal, you have to convert back to analog. Otherwise you cannot see any pictures or hear any sound. So you still have to convert to analog. So why do people want to do this extra step? Analog to digital conversion and then digital back to analog conversion, because there's some major advantages. Now let's look at the normal analog signals. Normal analog signals, if you transmit it over large distances, it will actually suffer from attenuation, which is called decrease in signal power. Alright, decrease in signal power. So in medical physics, we also got attenuation, but that one was called decrease in intensity. In this chapter called communicating information, we will call it attenuation as decrease in signal power. So why will there be a decrease in signal power? For example, if you are transmitting it through a cable, a wire, then there will be power loss as heat. Because your signal is alternating voltage, that means the current keeps going back and forth. So as it goes back and forth, it will dissipate energy as heat. So when it suffers from attenuation, you will see that the original signal becomes smaller, right? Agree? But this signal, when it's too small, it will be useless. So before it becomes too small, we have to amplify it if we haven't reached the destination. So when we amplify it, it will go into an amplifier called a repeater amplifier. But when you enter the amplifier, you don't forget, within your wire there is noise. And noise here being also the alternating voltage due to EM radiation that induces a voltage. For example, when the atoms vibrate, there is a movement of charge, so they also will generate EM radiation, which will also cause EMF to be induced. So you will never escape from noise, which is the voltage, stray voltage, which will add on to the voltage due to your signal. When you add on, the amplitude will be varied a little bit, so you will see jagged lines here. And these jagged lines, that means the signal, instead of a smooth curve like this, it will still have the same shape but with small jagged lines along the line. So what will happen is, everything will be amplified when they enter the repeater amplifier. Not just the signal, but because it already added to the noise, so even the noise gets amplified. So what you will get is an even more noisy signal. And if this one goes again and suffers from attenuation, and we have to amplify again, then you're going to add even more noise. So if you keep getting amplified many times, the signal will keep getting noisier. So at the end, you get too noisy. But digital signals won't suffer this problem. You know why? Because digital signals, when we want to transmit using ones and zeros, we also use high voltage to represent 1, low voltage to represent 0 . Because the ones and zeros, you must use something to represent. You're either high voltage, low voltage if you're using electricity. If you're using optic fibers, you can use light on and off to represent 1 and 0. So either way, you still have to represent the 1 and 0. If the alternating voltage here is I convert it into ones and zeros, that means it's either high voltage or low voltage, and I transmit it over large distances, it will still suffer from attenuation, because if it's voltage, there will be current, there will be power loss as heat. And what will be inside the wire? Also noise, so you will add on to the signal, so your resulting voltage has always these jagged lines here, can you see? And it will be amplified, but because it is digital, it will go into a regenerator, not a repeater amplifier. Now, a regenerator doesn't just blindly amplify everything. Your repeater amplifier just amplifies everything, but your regenerator, as the name suggests, generates a new wave. Not amplify this, it generates a new wave. So how does it generate a new wave? When it sees this voltage, which is generally high with minor fluctuations, it knows the minor fluctuations are due to noise, because there's no such thing as in-between values. It's either completely high voltage or completely low voltage. So if it is generally high voltage with tiny fluctuations, they will just produce a high voltage with no fluctuation. If they see a low voltage with generally small fluctuations, they will also eliminate the fluctuations and then just produce a clean signal. So it reproduces or regenerates a new signal based on the information that it reads. So that way, your new signal is completely free of noise. So this one can go to a next regenerator if it is traveling very, very far, and again they'll produce a clean signal. So you will never get noise. Do you understand? So the first advantage of digital is that there will be no noise. Now, what is the second advantage of digital signals? Now, digital signals, as we will learn later, you will see that they will only sample the data here at regular intervals, and each data is represented by ones and zeros. Between each samples, there will be gap. They don't take the whole information, they will sample at regular intervals only. And then they try to predict how the graph looks like. So in between samples, there will be empty time gap that you can use to put in extra bits of information like this to use to check for errors. Why you can put in extra bits of information? Because between samples you have gap. So you can put anything you want in between them. But for analog, there's no gap, because you continuously, whatever you have here is the whole thing you're going to amplify or send. There's no gap. So that is the second advantage of digital. So what is the disadvantage of digital signals? Same thing, like the cost. Because you will need extra circuitry to convert from analog to digital. So we call extra circuitry is required for ADC, and then later on DAC, which is digital to analog conversion again. Why? Because our speaker, our TV, all this must still be analog signals. How you transmit and how you store can be digital, but later on you still have to convert it back into analog. Understand? Now, in digital transmission, we will use binary codes to carry the information. And binary codes, as you remember, or maybe you've heard of, is ones and zeros, right now. So how did that binary code come from? So I'm going to teach you what it means by binary and how you can convert a decimal notation, which is the numbers that we use every day, into binary codes. Example, Now, with the numbers that we use are often called decimal notation, because if let's say I have 4 spaces for you to write any number that you want, I will say, can you give me a 4-digit number, right? So digit comes from decimal notation. If I'm talking about binary, I won't say 4-digit, I will say a 4-bit word. But if it's decimal notation, I will say 4-digit. So can you give me 4 digits? Can anybody give me 4 digits? So let's say you gave me 4731. So I write down 4731. Now, do you realize that you could have easily chosen any number between 0 to 9 at each place? Right? Because any digit means it will be from 0 to 9. So 0 to 9, isn't it 10 possible numbers? Correct? 0 up to 9 are 10 possible numbers, right? Which is why it's a digit, because deci means 10. Correct? So actually, what do all these spaces represent? Each of these places as a ranking. The ranking is like this. This will be 10 to the power 0. 10, why? Because it's decimal notation, which is 10. So 10 to the power 1, 10 to the power 2, 10 to the power 3. So when you write 4731, it is actually the same as 4 times 10 to the power 3 plus 7 times 10 to the power 2 plus 3 times 10 to the power 1 plus 1 times 10 to the power 0, which is 4000 plus 700 plus 30 plus 1, which is your 4731. Same number, right? Why? Because this, why is this the same answer? Because this method is to convert into decimal notation. Since this is already decimal notation, that's why you get back the same number lah. We're going to use this method to convert from binary to decimal now. Okay? So let's talk about that binary notation. Now, if I have 4 places here, I will ask you for a 4-bit word. Now, binary means how many? Bi means how many? 2. So there are only 2 possible combinations. If you start from 0, it will be 0 and 1. So you can only have a number between 0 and 1. That's it, because it's binary. With a decimal notation, you got 10 possible numbers from 0 to 9. But binary only got 2, so you got 0 or 1. Now, can you give me a 4-bit word?
0, 0, 0, 0.
Alright, so since you can't give me a good number, I will give you lah. So let's say the number is 1011. Alright. Okay, 1011 is way better than 0000. So 1011, what does it mean? Now again, each of these places has a ranking. The ranking will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So why I use 2? Because it's binary. So this number 1011, if I want to convert into decimal notation, it will be actually equals to 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0, which is 8 plus 0 plus 2 plus 1, which is equals to 11. In other words, a binary number of 1011 is the same as a decimal of 11. So you will need to know how to convert from binary to decimal, and later on decimal to binary as well, because we are going to use it for analog to digital conversion. Analog digital conversion, we will use decimal notation, convert to binary. And then later on, from digital back to analog conversion, we will convert from binary back to decimal. So what is the shortcut here? So the shortcut, if you want to remember how to convert, is, do you realize that this number, let me show you. This number here is 8. This is 4. This is 2. This is 1, right? So the magic number is 8421 to convert from analog to digital and digital to analog. Anyway, in your syllabus, you will only learn about 4 bits. We don't learn more than that lah. But of course, you can always expand the idea to involve 8 bits, 12 bits, 16 bits, or how many bits or so. But it's going to be very tedious. So we limit it to 4 bits. So remember this number 8421. Let's look at the next slide. Now let's talk about the magic number again, 8421. Now if I wanted to convert, let's say starting from analog to digital, so let's say this is analog, which is decimal notation. I wanted to convert to digital, which is binary notation. Let's start with a number from, give me a number between 0 and 15. 15. Now, what would be the binary number to represent 15 in decimal? Now, the technique is to see what we need to add up to get 15. So it will be 8 plus 4 plus 2 plus 1. Correct now? 8 plus 4 plus 2 plus 1 gives you 15. So therefore, the number will be 1111. Okay, give me another number for decimal between 0 to 15.
0.
Not 0, please. Because 0, okay, if you insist 0, then it will be 0, 0, 0, 0, 0. Okay, never mind. So that means we don't need any numbers to get 0. So you get 0, 0, 0, 0 lah. Can you give me another number in between them? 7. If you give me 7, what must I add to get 7 here? 4 plus 2 plus 1. So your number will be 0, 1, 1, 1. Give me another number. 10. So what must I add here to get 10? 8 plus 2. So your number will be 1, 0, 1, 0. But you can also work backwards. You can also change from binary to decimal. Now, can you give me a binary number, 4-bit binary number? 0, 0, 1, 1, 0. Okay. Now, what will we get is we can add up this and this only lah, because these two don't have much. So this plus this gives you 6. Okay. Now, can you give me another binary number? 1001. So that means we must add up this and this. So this gives you 9. Can you see that?
69.
Okay. Now you will notice that the smallest combination you can have if in binary will be how much? 0, 0, 0, 0. And then the biggest you can have is 1, 1, 1, 1, right now? That means between 0 to 15. So what does it mean? From 0 to 15 means how many possible numbers can we get? 16 right now, because 0 to 15 right now. So you see, the more bits you use, the more numbers you can have. Example, give you a next slide. Now, when you have a binary number of 0, 1, 1, 0, for example, this number is called the least significant bit because it represents the smallest number 1. This number here will represent the most significant bit because it's supposed to represent the number 8. So if they give you a 4-bit word, for example, they ask you to label the most significant bit, you label the leftmost. The least significant bit, you label the rightmost. Because it all represents a number 1, 2, 4, 8. So let's say we want to use a 4-bit word for digital signals. Remember, each of these positions, you can either write a 1 or a 0, right now? Either 1 or a 0, correct? So how many possible combinations can you come up with? That means you can start from 0, 0, 0, 0, then 0, 0, 0, 1, then 0, 0, 1, 1. You can go on until finally you get 1, 1, 1, 1, right now? So how many possible combinations can you get? You get 16. You can use a bit of maths. That means each of these places, you can have 2 possible permutations, right now, either 0 or 1, right now. So the total number of combinations will be 2 times 2 times 2 times 2, which is 2 to the power of 4 possible permutations, which is 16. So what it means is, if my digital is using 4 bits, I can divide up my signals into 16 levels. But if I choose to use a higher number of bits, let's say I use 6 bits. So I will have a total number of how many permutations? 2 to the power of 6, which is 64 possible permutations. Correct not? Which will start from 0, 0, 0, 0, 0, 0, and end with 1, 1, 1, 1, 1, 1. So I will get 64 possible levels from 0 to 63. So why is that important? When you convert analog to digital, you will need to decide how many levels you want to divide your data. The more levels you use, the more accurate you are going to get later on when you convert from digital back to analog. Give you an example, next slide. Okay, now let's say I want to convert analog to digital and digital back to analog. Now, my analog signal it is like a continuous variation, right? Like this. But if let's say this was your voice, let's say you wanted to record your voice and put it on a CD, you would use a microphone to convert your voice into electrical voltage, right? Remember the piezoelectric transducer? It will convert your sound waves into alternating voltage. So you will get the alternating voltage, but do you realize that this is not really alternating because there's no negative values, all these are positive values? Okay, let me tell you, because they did not show you the entire story. The entire story was like this. Originally, this waveform was from alternating voltage. That means if your axis was somewhere here, I'll show you. So let's say your axis is somewhere here. This is your axis of V versus T. This is originally the waveform, which is an alternating voltage. Can you see that? If I plot V versus T. But when I want to convert to digital, I will take out the waveform. So I take out the waveform means I take away the axis. I don't want the positive and negative values first. I take out the waveform, which is this shape. And I will divide to how many volts depending on how many bits I want to use for digital conversion. Example. Let's say this waveform I want to convert by using 4 bits. So if you use 4 bits, remember that you got how many possible combinations? 4 bits will be 2 to the power of 4, which is 16 possible combinations, which starts from 0 all the way to 15, right now? So therefore, you notice they divided up this signal from 0 to 15. If I wanted to use 6 bits, then I will end up having 2 to the power of 6 with 64 levels. So the same waveform, which is this, I will divide to 64 parts from 0 to 63. Agree or not? So these numbers here actually represent how many bits I'm actually using for conversion. If I'm using 4 bits, my value will be 0 to 15. If I'm using 6 bits, my value will be between 0 to 63. Now, which would be better? 0 to 15, the intervals, the gap between the intervals will be pretty large. But 0 to 63, all of the intervals will be very close to each other, right now. So when you use more bits, you will end up having closer intervals, which will actually result in better reproduction later. Do you understand? Okay? So this is a consideration. How many bits to convert? The more bits you use, the more levels you will end up. So each level, the separation between them will be smaller. Now, why is this important? So I explain to you. Now, let's say I use 4 bits here. As you can see, they use 0 to 15. During conversion from analog to digital, they will actually sample at regular intervals. Like in this case, they sample every 125 microseconds. So at 0 seconds, they sample this. Now, if you look at this value, this is actually slightly more than 8, which is, let's say, 8.4 or 8.2. But because your binary is only between 0 to 15, which is 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, there's no 8 point something, right now. So they will just ignore the decimal. That means when you read as 8 point something, you don't have point something, so you just read it as 8. But if let's say the second sample here, you're supposed to read it as 12.7, for example. But for binary, there is no decimal. So therefore, you will just read it as 12. So it's not rounding up or rounding down. It is just ignoring the decimal place. That's what we're trying to say. Okay, so just ignoring the decimal place. Now, after you have sampled every 125 microseconds, so these are your values, then they will convert into binary. Binary as in binary numbers. So how did they convert? Remember the magic number 8421? So 8 volts is equivalent to what number here? 1000. There. Your 1000. The next sample is 12 volts, which is 1100. 14 volts will be 1110 here. So you continue until the end. So now you have all your data in binary numbers. And when you have your data in binary numbers, you can transmit it either using optic fibers. 1 represents light turning on, 0 represents light turning off. You can use high voltage, low voltage if you are using electricity. So you can do that. And if you store in your CD, you call the process burning a CD, right? So why do you call burning a CD? Because the CD normally has a reflective surface. When you burn it, you actually shoot out a laser to darken that area. So a 1 means the laser will not darken the area, it will remain reflective. 0, the laser shoots up and darkens the area. So that means within your CD, you have areas that are reflective and not reflective, and they're very close to each other, which is why it behaves something like a diffraction grating, but it reflects the light back to you. That's why when you look at the CD, it looks like a rainbow colors. Do you understand? So you can store it in 1s and 0s, but when you want to play it, you will still have to convert to analog. How do you convert into analog? So the CD reader, your drive, will start to read it. How does it read it? It shoots out another laser for reading. That light is just for reading. It does not darken the disc. When it hits the reflective surface, it comes back to the detector, so it reads as 1. If it shoots out and hits the darkened area, it will be lost, so it calls 0. So that means the computer can interpret the 1s and 0s by reading your CD. But then, you will get back this up. And it's now the time to convert back into analog. Because if you want to pass it through your speaker has to vibrate. So it needs an alternating voltage to vibrate. So how does it get the voltage to vibrate? It reads this value. So how does it read? You want to convert to analog. So when it reads the disk and detects it's 1000, it converts back using this magic number, the voltage. So 10000 is 1000, which is 8 volts. So it produces 8 volts, but it holds the voltage until the next sample comes along, which is 125 microseconds later, which produces 1100, which gives you 1100, so 12 volts. So it goes up to 12 volts and holds it again until the next sample comes at 1110. So 1110 will be 14 volts, so it goes up to 14 and holds it. So by producing the voltage and holding, producing voltage and holding, producing voltage and holding, you will get back a recovered analog signal. But this recovered analog signal will never ever be identical to your original analog signal. It will never get back the same. After digital conversion and back to analog, your signal will never be the same. But does it make a difference? You will not be able to detect the difference if you do it as accurately as you should now. So how do I make it more accurate to convert from here to here and back to here? There are 2 things you can do to improve your quality. Number 1, you can increase your sampling frequency. That means you don't wait so long, 125 microseconds to sample. You can sample half the time. At every half the time you sample, then you won't have to wait so long. So this signal will show more variations. Another thing that you can do is you can use more number of bits. Because when you use more number of bits, let's say you use 6 bits, which is 64 levels, you still won't get any decimal, but when you have to round, you're only dropping a little. Now from 7 point, let's say this one 12.7, if you drop to 12, it's going to be a big drop. That means you are distorting the signal. But if let's say it drops from, if you got 64 levels from 0 to 63, if you are dropping from 63.7 to 63, it's only a very small drop only, because the intervals are very close to each other. So you will get less of a distortion. So higher number of bits and also higher sampling frequency will give you a better quality. But there is always a limit that you can detect. If you do it more than what you're supposed to, you will get a better reproduction, but it will not make a difference to us. We cannot see or hear the difference anymore. What you will merely do is you occupy more space. What do you mean by occupy more space? Because every time you convert from analog to digital, when you are sampling, you are actually converting into bits, and that is actually limited by the space on your CD. For example, a CD has maybe 700 megabyte storage. What it means is 700 megabyte is 700 times 10 to the power of 6 bytes. And 1 byte is equivalent to 8 bits. Why is 1 byte 8 bits? It is just like why 1 dozen is 12. Do you know why 1 dozen is 12? So you also don't know why 1 byte is 8 bits. It's just a grouping. They just set it as 1 byte is 8 bits. So if you multiply by 8, so these are the total number of bits available. So every time you have these ones and zeros, you are using 1 bit from here. So if you have more sampling frequency, that means you get more bits for 1 song. Which means to say you will occupy a bigger space within your CD. Or if you use more bits for each sample, let's say instead of using 4 bits, you use 6 bits. Every time you sample, you occupy 6 bits instead of 4. So you will also occupy more space on your CD. So therefore, we never overdo things. We will only do up to how much we require. So what is the general idea? We will see it in the question now. So how do we determine the best number of bits to use and what is the best sampling frequency? So what we will do is just recap what we have done in the question just now. If let's say your sample consists of low frequency and high frequency, then your interval or the time interval between the samples, you must choose the shortest peak to trough interval. So that your sampling interval, if it is smaller than this time, then you will be able to catch every change. But if your sampling interval is very, very far apart like this, you will miss the changes in between, like for example, because the changes happen in a shorter time than this sampling. So you always find the shortest interval between a peak and a trough, and then you make sure your time between samples must be shorter than that. Then you will catch every single change. Understand? So once you know the time here, for example, let's call this T. How did we find is you can find the frequency as 1 over a time shorter than this, right? Okay, I'll show you what happens. Now, if you take the time between a peak and a peak, that is called period, right? But if you take the time between a peak and a trough, isn't it half a period? So let's call this time half a period. Now, to catch every change, you must take a time smaller than this. That means your time must be smaller than half a period, right? So if the period of this highest frequency component is T, then the frequency of this is F, right? If you take 1 over T, agree? But if the time that I'm taking is half the period, what happens to the frequency? When I halve this, better write nicely, this is frequency, this is period. So if I find half the period, the frequency will become double, right? But since I'm taking a time less than half the period, the smaller than this, so my frequency must be slightly more than double the highest frequency component. In other words, the sampling frequency must always be a bit higher than 2 times the highest frequency component in your sample, in your analog signal. So you find the highest frequency in your analog signal, you times 2 and make sure your sampling frequency is at least slightly bigger than that. Then you will catch every single change. This is what Nyquist said. If you look at the next slide. Now, according to Nyquist, in order to be able to recover the analog signal, that means you don't realize any loss from the digital conversion, you have to choose a sampling frequency greater than twice the highest frequency component, as what I proved to you just now. So therefore, example, in a telephone system, the highest frequency that we are actually allowing is 3.4 kilohertz. So that means the analog signal has a highest frequency of 3.4 kilohertz. So your sampling frequency must be a bit more than double this. So double this, you get 6.8. So slightly more, they choose 8. Now that example, if you're talking about CD, playing music, the highest frequency we can hear is 20 kilohertz. So your sampling frequency, you times 2, which is 40, and slightly higher. So you use 44.1 kilohertz. So that way, we will be able to get every single change. And just a recap, what about the number of voltage levels or the number of bits? Always remember that if your signal has big variations in voltage and small variations in voltage, in order to get every change, we must choose the voltage interval from the shortest peak to trough height. So once we know the shortest peak to trough height, we take the voltage interval slightly shorter than this so that we can catch every change. So instead of like this, slightly smaller voltage interval, then we will catch every single change. Understand or not? So that way, we will be able to get a good reproduction of the analog after digital conversion. Alright? So that is how you do it.